In this video, we're going to work out the volume underneath this surface, within this specified region. So this region is a circle of radius 1, and it's everything all the way to infinity, Okay, so glancing at this, here you can see there's some sort of circle here, and the region in which you're integrating over is a circle. So it makes sense to think about polar coordinates. So to convert this into polar coordinates, picture this in your mind. So to convert this into polar coordinates, picture this in your mind. So you can see r squared exists in here, and then this dA becomes this thing here. So when you put r squared into here, it will then give you this. So now it's just a matter of integrating this, but we need to come up with our limits of integration. So looking at this, we've got one integral, and then we've got another outer integral here. So this inner integral here is talking about dr. So it's going to be r equals something, and then r equals something. The outer integral here, it's going to be talking about theta, so it's going to be theta equals something. So going back to here, the region in which we're integrating over is given by this. So we always radiate, the radius is always radiating away from the origin. But the thing is, we are integrating from 1 to infinity. Radiates from the origin, but the thing is, we are integrating from 1 to infinity. It's radiating away from the origin, but we are integrating from 1 to infinity. From 1 to infinity. From 1 to infinity. So r would be this. R would be from 1 to infinity. And then the angle, you're scanning the angle. Hang on. So if you look at the angle, you're scanning from an angle of 0, and then you're moving around like this. You're scanning from an angle of 0 to an angle of 2 pi. So theta would be from an angle of 0 to an angle of 2 pi. So that will then take us to here. So now it's just a matter of integrating this. So hang on. So now it's just a matter of integrating this. So integrating this, this r here gets multiplied to the top. So that will then give us this thing here. So notice that this r is a derivative of r squared-ish. So you know it's going to be easy to integrate. Use whichever method you want. You could use substitution, but don't bother. When you can glance at this as a derivative of r squared, then just do it in your mind. Currently, looking at this, visualize it like this. Currently, it's like this. To the power of -2, and then you've got this r. So visualize this thing as this. Notice that this thing is a derivative of this thing here. So if you're trying to integrate this, make it one notch higher than this. So make this to be your initial guess. One notch higher than this. -1. So now when you differentiate it, it will then, well, the -1 comes down. Just remember, all this exists in your mind. -1, the bubble stays intact. 1 plus r squared. The power gets minused by 1, and then times the derivative of the bubble itself, which will be 2r. So when you tidy this thing up, it will look like this: 1 over 2r over, and then this thing here, which will be 1 plus r squared. You see, this matches up with this. The only difference is that you've got a -2 here. So go back, negate the negative by sticking a negative in there, and negate that 2 by sticking a half in there. So when you integrate this, it will then give you this thing here. Okay, well, do whichever way you want. You could use substitution if you want to, but when you integrate this, it will then give you this, and we're integrating from r equals 1 all the way to infinity. So now we've got to evaluate this thing here. Now remember back in calculus 2 when we were doing improper integrals, if you're trying to find out the area all the way to infinity like we are here, technically, to be technically correct, you have to integrate it to b. You have to integrate it up to b, and then take the limit as b tends to infinity. So you have to slide this b all the way to infinity. But do that in your mind. When we come to do this, let's be lazy and just stick infinity into there. It will have the same effect. By right, you should integrate it up to b, and then slide b all the way to infinity, meaning you take the limit as b tends to infinity. But let's be lazy and just stick an infinity into here. So when you stick the infinity into here, meaning when r is really big, this thing here is going to be really big, times 2 is going to be really big, and then a number divided by something very big is going to be 0. And then you've got to take away, and then you put this into here. That will then give you minus a quarter. So if you evaluate this whole thing here, it will then give you this thing here, which is a quarter. So now when you integrate it with respect to theta, it's going to be theta over 4, from 0 to 2 pi, from 0 to 2 pi. So now put this into here, it will give you a volume of, it will converge to pi over 2. So you can say the volume is pi over 2. Okay.